Welcome back to EE 386. By now you will have taken your midterm, so congratulations, you're all done with that. And that means that we are in the second half of the semester. So it's time for transfer functions and also frequency analysis. So that's really some interesting stuff, so I hope you're excited for that. So what we're going to be doing the first half of this second half of the semester is doing more control design. We're going to be doing that through transfer function formats, and that means that instead of designing a control algorithm as we have been doing it with U of t and being in the time domain, we are going to be in the Laplace domain. We're going to be designing a compensator block. So compensator block is GC of S. We're going to first cover the case of stability. And of course, we're going to adhere to that minimal order design technique, so we'll go through that procedure. And then we have various methods to explore to design control gains. And this is the bare minimum of what we're going to cover in this lecture. We'll see how far we get with examples and such. Okay. So this is class number 12 out of the summer 2020 series. Class number 11 would have been your midterm, and there will be a separate video for the midterm review. This is just lecture and new material here. Okay, so previously we had been talking about transferring from the time domain to the Laplace domain, and we covered that in our last lecture, which would have been class number 10. And going back and forth between these, and also how we had previously represented systems as differential equations, and now we're going to be representing them as transfer functions. So we went between taking the differential equation in the time domain, transferring it to the Laplace domain, and then forming that transfer function, which is a ratio here, format output over input. Okay. Previously, we had designed U of t, and now we're going to be designing GC of S. Okay, so GC of S is going to do the same job as our U of t. This is the compensator block. It is really our control. It's our control block, our control algorithm, really, but it's a transfer function. Okay, so we just to repeat from last lecture, we had the standard block configuration, and that's again shown here, where we had a reference input, and this is all in the Laplace domain here. We had our system response here, y of t, that's our system output. We did have the control block, and it would take either feedback from y of s or the error, as I've shown here. So really, if we had a non-zero reference input, we would have an error here. And then we would produce that U of S signal here if we're in the Laplace domain. Okay. GP of S is our plant. That was previously just a differential equation. Now it's transfer function. Okay, but it's really the same thing. That's our plant, compensator block, control. So really, the orientation is very, very similar. The terms are different, and the look of each of these guys is going to be a little different. Okay. Now, you're probably wondering, well, we learned all this stuff. I've mastered it because I did really well in my midterm. That's great. Can we use what we've learned? Yes, we can. We just need to know how to apply it. So really, the first half of this lecture, I'm going to try and explain that to you. Is the characteristic equation still visible? Is it still useful? Yes, we can still use that. We can actually pick that out of our GP. We can still pick out our system roots, find our general solution, and this is the format we followed before with differential equations. With the transfer function, what we're going to do is, if we wanted to get back into that general solution format in the time domain, we could easily do that. We would take our transfer function, we would take an inverse Laplace transform, and then we could go through our evaluation. The other option is to take the transfer function, pick out the characteristic equation if it's visible, and this is if we are just evaluating a block by itself, okay? Just GP, say. And then we're able to follow this here. Okay. Now, why would I want to do an inverse Laplace transform? Well, it depends on what your transfer function is. If I have GP, it's already formed, well, I can probably just jump into this lane right here. But if I'm combining things, if I'm getting an equivalent equation, equivalent transfer function for this whole system, I may not have something that's as easily workable. It may have different parts to it, and I may need to do something like partial fractions to expand that out and then do the inverse Laplace transform. And then I can go through all of this right here. If it's even needed, I may be able to just arrive at a general solution in that way. Okay. All right, so just to illustrate, you remember we had these differential equations. Say that was our system right there, this top row. So we had a derivative and plus 2 single derivative y minus y equals 0. We were going through and transferring that into the Laplace domain. In order to do that, I just put a symbolic reference input r of t right here. So we were able to easily do this and form our ratio. Now, it's easy to go on this left side, go to our characteristic equation. We can just jump from this top row right to it, replacing every derivative with a lambda. So every power gets a lambda. And you should recognize this. This is very simple from what we've done so far. From the transfer function, so I already went ahead and formed the transfer function right here. Our characteristic equation is actually the denominator. Now, it doesn't matter that I have a 1 here. I might have an equation up here. That's totally fine. That does not change that the characteristic equation is just this denominator portion. So you'll see that these actually match. This is really the same system on both sides. We're just evaluating it in different ways. We have a characteristic equation over here and a characteristic equation over here. Here I have s's, here I have lambdas. It doesn't matter. The system roots will come out to be the same if you evaluate, the same equation, right? And so if we were to plot those on the complex plane, we've got one in the right-hand plane, because this square root of 2 is 1.414, if we were to calculate that out. And so we're going to have one root on the right-hand side, and then we're going to have another root on the left-hand side. So of course we can say that's an unstable system. Any root on the right-hand side, as we know, makes this an unstable system. Okay. If we wanted to take this a step further and just continue evaluating the system, everything we've done so far, we have the general solution we could find. So we know what the system roots are. We know that they are a real and distinct pair. So nothing repeated, nothing complex. So we can evaluate them in the general solution format for the real and distinct pair, or real and distinct roots. And if we were to plot that, it would be something like this. It's going to, whatever C1, C2 are, I left them arbitrary for this, and there would be different cases of this, but here are 2 cases where we have both are positive or both are negative. And so it's going to expand exponentially as time increases, just like that. So again, we can verify that is an unstable system. We can see it here, we can see it here, and if you know what to look for, you can see it here. Okay? All right. And again, previously we had designed the control algorithm U of t. It was a function of our system output. We could have time if we needed it. We had the derivatives as needed and as our measurable, and we had integrals if we needed them, if it made sense to have them in there. If we had, say, a disturbance or something like that. We could also use error. So I'm just going to put right here, or error, derivative of error, integral of error. It's the same kind of thing. So I'm just showing what we used before. So now when we design the compensator block here, we're going to have a different kind of form. It's not going to be an equation as before, differential equation. It's going to have a transfer function kind of look. we're going to have S's on the top, S's on the bottom, as much as it makes sense to do so. Okay, there is a procedure that we follow to pick out what we're going to use. Okay, I do want to make sure you know this, what we're talking about right now, this pattern we're about to discuss, is the stabilization case and no disturbance. This greatly changes the pattern every time. Okay, if you have a disturbance, your pattern will not look like this. Your procedure will be the same, but your pattern won't look the same. Okay, so that is the very first thing you need to know. Whenever you are doing a design, you need to know what your control task is. And that's really similar to what we did before. Remember, we would design U of T to be either like a addition of a stabilization U, a disturbance accommodating U, and such, set point regulating U's, you know, different things like that. But it depended on our control task. So the control task is very important. It's worth writing here. Okay, so that's the very first thing you should know. What are you doing? What are you designing your control for? All right, so let's talk through the general technique for designing a GC of S, okay? Again, this is what I'm going to talk through is the stabilization case. We'll go through different complex cases, but let's talk about this one first because it's the simplest. Okay, for the minimal order procedure, we'll have these trial designs. What we're going to do is we're going to choose our simplest version of what our GC might need to be, okay? We're going to set up our pattern to accommodate that. So for the stabilization case, I'm not going to need to do anything extra, and we'll talk about what I mean by that later. But I'm going to have, I'm going to always want to give myself at least one gain value. So I start off in the simplest case with a KC. We like to call it KC, or you can just call it K if you like. That is going to be my first parameter. Okay. Now I'm going to go ahead and try this out. I'm going to work through the algorithm and see if I can compensate my entire system, if I can stabilize things using just this GC. This will be my GC. Okay. And if that doesn't work, for any reason that doesn't work, I'm going to jump to one complexity up. Okay. So here, I am going to add a S plus some variable. I picked A here. I like to go A, B, C, D, and so forth on the denominator. Okay, there's a reason I put it on the denominator. You have to keep in mind as you step up complexity in this pattern that the denominator has to have a power of S that is greater than the numerator, or the numerator can be equal to the power of S of the denominator. Okay, so here my power of S in the denominator is 1 and the power of S in the numerator is 0, so we're okay here. Okay, as I step up, if this doesn't work, I step up the complexity one more time and I have a power of S 1 and 1. Okay, denominator and numerator power is equal. That's still okay, but I cannot have like a power of 2 and a power of 1, okay? So I can't put another S plus something up here until I have an S plus something else down here. Okay, does that make sense? Hope so. So if we were to continue this pattern, okay, we would need to make sure that we obey that rule. Okay, in order we have, to do that, we have a order of M sort of polynomial here on the top, and then we have an order of n here on the bottom, say for GC of S. Now I'm not meaning n as system order here because we are just talking about the compensator. We're not talking about the entire system, but say this did have n and m, just different orders, okay? Well, PC, our polynomial in the numerator, that has to be less or equal to the order of the denominator, QC, okay, that polynomial. All right, we have to obey this so that we can actually build it in real life, okay? That's needed for physical realizability. Now, you may be thinking, Okay, does that mean that I can just go into Simulink and I can do this? Yeah, Simulink will let you do some things that you can't really do. And that's fine. That's great for experimental purposes, or if you're building a block that is part of a larger system of blocks, okay? So there is really a need for that, and that's why they let you do it. But if we have a single block like this, we need to adhere to this rule, okay? And in general, in this class, we are always going to, if you're doing things correctly, you're going to adhere to this rule, okay? So example, don't do this. This is what I mean. Here I have a third order polynomial on the top, and I have a first order polynomial on the bottom. That's bad. Don't do that. So is this the pattern? Now I'm just going to repeat what I said before. Is the pattern correct for every single problem? And of course, no, that's not the case. Are you always going to adhere to this? Yes, you are always going to adhere to that. You can keep that in mind. But what we're going to do first is stabilization. This pattern that I've shown here is only for stabilization with no disturbance, okay? I want you to get this down first, and then we'll conquer the more complex cases. But you see what I've done here, where this is our least complex. We stepped up the complexity if that doesn't work. And we have an S plus A on the bottom. If this doesn't work, we now have the ability to add to the numerator. Now, one question you might wonder is, well, if I know I need to adhere to this, why don't I just keep adding to the denominator instead of ever adding to the numerator? Well, the numerator is a great place to add, and you'll see as you work problems, you'll see why. With the numerator, you're guaranteed to have a little bit more control over it. So if I add this S plus B to the numerator, I have my B variable now involved in the equation. And as we'll see shortly when we do examples, you're going to have the ability to stabilize stuff using this B variable, okay? The advantage is that because it's not in the denominator, I am not going to have an increase in my system order. So I'm going to have a system order increase for every time I add an S to the denominator of GC, okay? And then that means that I'm going to have to solve for another root. I am going to have a higher order system to solve. If I'm just evaluating by necessary and sufficient conditions, it's going to be another necessary and sufficient condition, at least one more to solve for, okay? So this is great. When you can do this, when you can add to the numerator, you definitely want to take advantage of that. That'll save you some work, okay? All right, so as we continue our pattern on, we have, we add to the bottom again, and then we have an order of 2. I have an order of 1 on the top, so if this doesn't work, I can add 1 more to the numerator and so on, okay? So this alternating pattern, again, stabilization, no disturbance, okay? We haven't changed this at all. This will be different for every different case you have. If you have set point regulation, this is going to look different. Set point regulation with a disturbance, that's going to look different from regular set point, and so forth, okay? We'll talk about that later, as I've said before. All right, so, but yeah, just to repeat that, more complex cases, we're going to talk about that later, and we do have a technique for that. This is called using the free S, okay? There will be free S's, multiple S's, and a single free S, whatever is appropriate, okay? And we can talk about how many to use, when to use them, and if how it changes the GC design pattern, okay? But quickly, why do we use this? Well, before we were talking about integrals when we designed, say, like a U of t that was for set point, or for command signal tracking. We used the error in that case, but we also included a type of integration for any kind of a disturbance, okay? So that integration is equivalent to an S on the denominator. We can do a lot with an S in the denominator. And in general, we'll take advantage of that, but there will be design rules when we need to add one and when we don't. All right, let's do an example. Okay, so GP of S. Okay, so let's say we have the system right here, all right? The two pieces you're going to need for information to do any problem like this, to design a GC of S, is, first of all, why am I designing GC of S? Here the control task is to stabilize the system. Control task would be set point, command signal, stabilization, and if there's any disturbance, that would also be part of it. The other piece of information you need to know is the block configuration. Again, if this is never given to you in a problem, if there's a problem you have and it's not specified, you can assume that you're using the standard block configuration. And again, standard block configuration a few pages back, but we'll just draw it up here real quick. So we have Y of S with our negative feedback. Actually, let's put the negative sign right here. We'll put a positive sign right here for R of S. R of S can be 0, and that is fine. It can also be any kind of reference signal. This is where our set point, our command signal would insert into our system. Our disturbance would be right here. It would have a summing junction, and the disturbance would come in here. And we would add U signal and the disturbance signal, and they would both be inputs into GP, because disturbance, of course, is an input to your system. It's just one that you cannot predict and cannot measure. Okay, so if we just examine this right here, we can see the system is stable and that our lambda, our single root, is actually -1. So I can see this just by looking at this guy. Now, the denominator, again, is our characteristic equation for GP. Okay. All right. So what do we want to do? We want to design GC of S. All right. So the first thing we'll do, knowing all the parts of our system, is to establish our trial design listing. Okay. That's going to be our pattern. All right. So the trial design 1 is going to be Kc, or you can write it as Kc over 1 just to keep that transfer function kind of format apparent. The second one, we'd have an S plus A on the bottom. Okay. Why do I put an A here? Because I want to give myself as much design flexibility as possible. I want to include control gains whenever I can, because that gives me more control over the final system. All right, so I have an order 1 and an order 0, so that means that I can step up the complexity in the numerator, and that's great. We'll see shortly why that's good. And if we were to keep going, we'll just do one more. And this is really just a repeat of what we had on the other page, but having them handy is good, just like that. Okay, so this is going to be trial design 1, 2, 3, and 4, just so I can reference them as we write. Okay, so what we're going to be evaluating for this, the calculations, is actually the characteristic equation for the entire system. Now, if you remember back from our previous lecture, we went ahead and found GCL. We derived that. We derived that by plugging in GP and GC and finding the closed loop transfer function here. And then we plugged in P sub P over Q sub P and P sub C over Q sub C for GC of S. So what we did is we found this formula right here. And then when we plugged that in and we simplified, we'll write QP. We're going to try and keep our order correct. Okay. This is from class 10 lecture. Okay, so one thing I do want to point out, even though I have written an equal sign, this does not mean that you can say GP times GC is P sub P times P sub C. You can't write out this right here as equivalent just because we have this equation. Okay, that's not the same thing. We took this, we plugged in the two ratios, and we simplified it. Okay, so numerator here are not equal. Okay, so that means that for the entire system, this is our characteristic equation. Okay, so we've got this guy handy, and we're going to call that QCl. And equivalently, we've got a PCl here on the top. Okay, so QCl will give us all of the poles for the entire system. Poles are equivalent to system roots and what we're talking about here with control design. And then PCl's roots are the zeros for the whole system. Okay. All right, so both of these are critical frequencies that we'll plot with Bode plots and such later. But the system roots are what are going to determine the stability. The system roots as being the poles. The poles will determine your system stability, okay, if it's stable or not. All right, so we want to solve QP, QC, plus P sub P, P sub C. So by setting QCl equal to 0, you can solve for the system roots, and we'll just leave them as S's. We won't bother plugging in lambdas here. Okay, so that means that here, P sub P over Q sub P is equal to 1 over S plus 1. Okay, so that means that P sub P is equal to 1 and Q sub P is equal to S plus 1. It's really handy if you write this out first. The sub P equations will not change because those are dependent on your plant. Your plant is given to you as part of the problem, and the plant doesn't change. But QC and PC, these are the ratios of the compensator block, what you're designing. These are going to change every time. So as you go through each of these trial designs, you'll want to repeat writing out what these guys are, okay? So let's try, and I'm going to show you the procedure to determine if this works or not. Let's try trial design number 1. GC of S, trial design number 1, okay? So if GC of S is equal to this KC, which is a gain I'm going to design, over 1, that means that P sub C is equal to KC and Q sub C is equal to 1. All right, now we already know that our P sub P and Q sub P, what those are. This was S plus 1 and this was a 1. And I just pulled those from GP itself. Okay, now what we want to do is plug in all of these 4 parts into this equation here. Okay, so let's examine our QCl. So P sub P times P sub C plus Q sub P times Q sub C equal to 0. Okay, so now we plug in our values. Okay, and we've got a 1 here. PC, we've got a KC, so that's a gain we can design. All right. QP is S plus 1, and QC is 1. Now let's simplify this, and then I want to point something out to you. All right, so we're going to simplify this. It's going to be KC S plus 1. And so if we were to write it in the descending polynomial kind of order, it would be this right here, KC plus 1, right there. Okay, so I'll point this out at least one more time, but you can see that if I were to plug in something more substantial for the numerator, so our numerator here was KC, but say I have like S plus A times S plus B, something like that, you could see that that would increase the system order. We had this part right here that's determined by the QP right here. But as we increase the order of our denominator, our QC right here, or our PC right here, you can see that we're going to have additional S's. Okay. The numerator's effect is not nearly as great as the denominator's effect. So this is why we want to make sure whenever possible, we add to that PC. With QC, say we'd have whatever the denominator is here, S plus 1, and say it was S plus A times S plus B. Well, now we have a third order equation portion right here. So even if that was second order and we did that, this one's far worse because we have the multiplier of the QP. Okay? All right, so whenever you are guaranteed to increase your system order whenever you have an S here in a QC. So it's not avoidable most of the time, but you know, if you follow our design technique, our pattern correctly, then you'll be doing the best possible case, the least amount of work possible. Okay, and as we know, less work means less possibility for errors, so that's always good. Less cost and all of that. Okay, so back to our problem. This is where we're at. So if we wanted to examine this for the necessary and sufficient conditions, so with respect to necessary and sufficient conditions, then we could write that S, actually our equation right here, S plus KC plus 1, we only have the one necessary and sufficient condition, that we have this portion has to be greater than 0. And we know that we have to adhere to that because we have a monic equation, positive 1 right here in front of the S. So as long as KC plus 1 is greater than 0, we're good. So that means I can choose any KC that is positive and it'd be fine. So that's quite a wide range. If we were to simplify this equation, really any KC that is greater than -1, okay? So any of those would work. So for example, KC equal 10 works. Okay, if we did have KC equal 10, our GC design would then become just like this. And you don't have to write the divide by 1. I chose to because I'm trying to just keep that transfer function format. Okay, so this is a really simple example. Let's do something a little more complex that we have to evaluate a couple of different trial designs for. So let's do this. How about GP of S is equal to let's make it something that is unstable. Do 13. And let's have an S plus 1 on top. Okay. And then we also assume the standard configuration. And then our control task is stabilization. So we want GC of S to stabilize the system. Okay, so as you know, first thing we want to do is write out our trial designs, and we can also pick out our P sub P and Q sub P just for easy plug into the equation. So I'll go ahead and write those first. P sub P is going to be the numerator S plus 1, and Q sub P is going to be the denominator S minus 13. All right, so if we were to do our trial designs down here, GC of S equals, again, same one that we used last time, and then we'll have KC S plus A, KC S plus B, S plus A, and if we wanted to keep going, we could. Okay, so let's try, and for easy referencing, I'll just put the numbers down here. Okay, so try number 1. So that means that for GC, we're going to have a P sub C is equal to KC, and the Q sub C is equal to 1. All right, so now if we try our Qcl formula, and I'm going to write that back out, we'll have a P sub P, P sub C, Q sub P, Q sub C equal to 0. So we want to go ahead and plug those in. All right, so we've got a, back up here referencing that, we've got an S plus 1, and a P sub C is KC, so plugging that in. And then we've got Q sub P, that's S minus 13. And we've got QC, and QC is 1. All right, so let's see if this is stable once we multiply it out. All right, so we have a KC times S plus a KC right here, and then we've got an S minus 13. And now when you work through these problems, you're going to have a case that is similar to this, and that is where we end up with an equation that is not monic. So you can see here that I've got KC plus 1 in front of the S, and then my other term is the KC minus 13. Okay, what you can do in this case is you can divide through by KC. If you divide through by both terms, then you can determine necessary and sufficient conditions. So let's do that. So we've got S plus KC minus 13 over KC plus 1. So we just divided through. Okay, and that's still set equal to 0, because if we divide through by KC plus 1 over here, provided that KC is not negative 1, we do have to write that, because we don't want to break the rules of mathematics and divide by 0 there. So we know now that for the necessary and sufficient conditions that we have to have a KC minus 13, KC plus 1 that is greater than 0. So this has to be a positive value right here. So we can come up with a KC that works. Let's say, for example, KC equals 20. KC equals 20 would leave us with a 7 on top and 21 on the bottom. Okay, so it would be 1/3, and that's greater than 0. And in general, as we increase KC in value, we should see the left-hand plane roots move further out into the left-hand plane. It should be stable in this case, and this would work. Okay, as long as we adhere to that necessary and sufficient condition. Okay. Now this was another example. This was a little bit more complex, but I really want to do one where we do multiple trials of something that doesn't work. So let's try another example. All right, so here in this scenario, we will have, let's just say we have a 1 on top, and we'll have an S s minus, let's do 5. Okay. And then again, I'm going to use the standard configuration. We'll do an example where we don't at some point. And we also want our control task to be stabilization. Okay, first thing again we're going to do, P sub P is 1, Q sub P is the S minus 5. We just pick those out and write them out so they're handy. You might want to choose to write Qcl here at the top, and that way you can keep referring to it if you continue to have space on your paper. Oops, wrote a Q. Don't want to do that. All right, there we go. And that, of course, has to be set equal to 0. All right, and then we want to make sure that we have our GC of S trial designs ready. So we want to start with that KC over 1, KC S plus A, and KC S plus A, S plus B. Okay, let's try number 1. All right, so what we're going to do is plug in. So we'll write P sub C is equal to KC, and Q sub C is equal to 1. We'll plug into our QCL. All right, so P sub P is 1. P sub C is KC. And then QP is S times S minus 5. QC is 1. Okay, you can see that we don't have a lot of control over the system because we just have KC as our design variable. All right, now as we simplify this, we have KC plus S squared minus 5S equals 0. Now if I wrote this in the correct order for like descending polynomial order, we have this right here. Now, examining the necessary and sufficient conditions, I'm really pleased with this example because we can see that this design, trial number 1, does not work. So it fails necessary and sufficient conditions. There is no way that I can pick, I seem to have lost my KC. Whoops, KC. But same thing, continue saying that sentence. There is no KC value that I can choose that will stabilize this. I have to have control over this middle term, and I don't. So you can see that this is not greater than 0, even if I choose a KC that is. So KC has to be greater than 0, but then the negative 5S term fails. All right, so if anything fails, if any reason, for any reason this doesn't work, we have to step up our next trial design. Step up our complexity, that is, and try the next design. All right, so PC in this next case is going to be still KC, but we are going to have a QC that is less trivial, so S plus A. Okay, now I have KC and I have A involved in the equation. So let's write out our QCL. All right, so for QCL, we're going to plug in P sub P, and that is 1. Then we're going to plug in P sub C, and P sub C in this case is KC. We're going to add that to our Q sub P, which is S times S minus 5, and that's going to be multiplied by this QC, which is S plus A. Okay, you can see that we are going to have a higher order equation because I have more S's multiplied together. I should have a third order equation at the end of it, whereas we had a second order before when we didn't have any S's in the denominator. Okay, so you can see that's our penalty we have for doing this. We have more control over the equation, but we are increasing the system order. System order only increases when QC increases. So from here to here. That's what's happened. System order increased. Just make that completely apparent. All right, so we want to go ahead and FOIL this out. So I'm going to have an S term in front, and then we'll have S squared minus 5a. You can do it in any order that you want. And then we always just combine at the end. Okay. And I'm going to write in the very end of this here, we have S cubed, and then I have a minus 5 S squared, and then we have a minus 5a times S, and we have our Kc at the very end. Now, I have 3 necessary sufficient conditions here. So I have to make sure that this guy is positive. I have to have this right here times this be greater than this. These both have to be positive. You can combine those and really just end up with 3 necessary and sufficient conditions. But so you can see that there's a possibility that this could work. Let's go ahead and examine that. I'm just going to write them out here. So necessary and sufficient conditions for this case. A minus 5 has to be greater than 0. We have to have negative 5a be greater than 0, and that's from the second term. And then we have to have our third one, which was the first coefficient here at a minus 5 times the next one, the negative 5a. That has to be greater than the last one for our third order. And that's our third order necessary and sufficient condition set. Okay, so can we do all of this? Let's see. So as we go through, simplifying, okay, that seems reasonable, right? And then we'll end up, to get rid of this negative sign, we're going to end up switching the sign here. So we would have 5a less than 0, and that implies that a has to be less than 0, because if we divide 3 by 5, then 0 divided by 5 is still 0. Okay, so we can say that we don't really even have to evaluate this third guy. These two conflict. There's really not a way that we can satisfy both of these. Okay. All right, so that means that this design doesn't work. Okay, so that means that we're going to have to step up the complexity to our third trial design. Okay, for number 3, we're going to have the Kc S plus B over S plus A. Okay, we'll just write it out here. So that means that our P sub C is equal to Kc times S